Hey, you guys can hear me, right?
Certainly.
Yeah. Just a minute. Oh, you can hear me, right?
Yes, you're clear.
Okay. So in today's class, we will basically um, try to complete on the presentation part. So the things related to uh, the flight mechanics will be taught today. So uh, the autonomous vehicles. Uh, Another part is the one is the ground autonomous vehicle that we discussed yesterday. Today we'll be discussing a little bit of core concepts regarding the aerial autonomous vehicle. So in the aerial autonomous vehicles, there are things that are actually getting governed by there are things that are governed by these scenarios. So uh, that is what we will be discussing in today's class. So majorly in yesterday's class, we particularly discussed about the autonomous vehicle, the ground autonomous vehicle in detail. So what are things that are important, what kind of sensors are important, what are the significance of each sensors and whatnot. So these things are the ones that we discussed in yesterday's class. In today's class, we will try to complete the other PPT that is there regarding the aerial autonomous vehicle. So the ground autonomous vehicle is complete. The aerial autonomous vehicle will be completed today. So probably in tomorrow's class, we will be doing uh, the analysis, the complete analysis of, yeah, the complete analysis of the system into ANSYS. So as we did it for the electrical vehicles, what all analysis we did it for the electrical vehicles. Similarly, we will be doing it for the uh, um, similarly, we'll be doing it for the ground vehicles and autonomous vehicles as well. So in the autonomous vehicles, we'll be majorly particularly doing the analysis of the air autonomous vehicle because the ground autonomous vehicle and the ground electrical vehicle are basically of the say similar trends. So what all things we actually discussed regarding the autonomous vehicle, we particularly have been discussing from the first class about the ground vehicle only. So uh, it is our I can say it's our responsibility to also touch upon the aerial autonomous vehicle as well. So particularly we'll be discussing a few concepts regarding it, and then in tomorrow's class or maybe by the end of today's class, we'll be trying to sum up the uh, aerial autonomous vehicle answers portion also. So we'll start the initiate the aerial autonomous vehicles portion on answers. So that will be the end of the course class. So that's how we'll be planning it. So let me first share my screen and thereafter we can just forward. Yeah. Mm. I hope my screen is visible. Vishal, could you please confirm? The phone host from XLR, can you please confirm it? No? The concerned person from XLR, can you please confirm it? Am I audible? Uh, uh, can anybody from the uh, uh, students confirm it that am I audible or not? Can you please say? Oh, thank you. Uh, We'll touch a little bit uh, on. So yeah, this part we discussed yesterday, right? So this was something that we discussed in yesterday's class regarding autonomous vehicles, its different types, introduction, fundamentals, then the agenda, the different types of autonomous vehicles, race evolution, SE principles, these things. Then the key definition of autonomous vehicle, what is the difference between the driver and the assisted vehicle, the key technologies of powering autonomy, the sensor technologies, which are the eyes and the ears, like camera, LiDAR, radar, and ultrasonic sensors, the perception and machine learning, which are the core objectives, classification, thematic segmentation, and sensor fusion. Then the mapping and localization, which include the LD maps, SLAM, and GNSS designing fusion. Then it included the planning and control, the brains of autonomy, which included route planning, behavior pattern, trajectory generation, low-level control. So that got subcategorized into global level and local level categorization of the brain autonomy. Then we discussed about the evolution of the vehicle automation. So from the early 1950s to the uh, current times and to the future scale deployments. Then the early milestones. We discussed the modern era. We discussed the commercial research acceleration. We discussed the research trends that are there. So then the SAE level, which included the zero and the one level automation, or the foundational automation, then the partial driving automation, then conditional driving automation, in high and full driving automation. So human factors and safety considerations, which included human the loop challenges, full automation, safety pillars, which included enhanced safety, increased mobility access, economic efficiency, reduced congestion, environmental benefits. So technical and commercial drivers, which included advanced sensors and compute, AI and machine learning breakthroughs, ride hailing and logistics demand, potential cost savings. So then we discuss about the goods and the logistics and goods movement. So this was the complete thing that we were discussing in the last two classes. So we discussed everything in detail. We also took time to understand the technical competencies that are required for electrical vehicle design, the ground electrical vehicle design, and its principles regarding it. So these were the things that we did in the last one. Today's class we'll be discussing about the aerial autonomous vehicles. So the aerial autonomous vehicles are the drones. Just a minute. Yeah, so the hidden autonomous vehicles are nothing but the drones. So the functioning principles of the drones and how the drones are actually operating. So the basic underlying principles will be recording by the fundamentals of flight mechanics for the UAVs. So uh, so basically in the UAV is nothing but unarmed aerial vehicles. So unarmed aerial vehicles are also a type of autonomous vehicle because you don't need pilots or any controlling persons sitting or controlling it. You just feed in the mission, and the UAV will be capable enough to go from point A to point B without any hindrances, right? So uh, the complete autonomy of the vehicle is being achieved in that sense because here as well your complete motion from point A to point B is being achieved by the autopilot that happen to be the sole and controller for the ground autonomous vehicle. Similarly, here also there is an autopilot that actually is responsible enough to a have a basic motion from point A to point B uh, without any human intervention. You just feed in the mission, you plan the mission, and it will go from point A to point B. So, be it a logistics drone, be it a uh, 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 mission-based surveillance zone, be it a loitering munition, be it anything. So, all the things actually work on the autopilot, and no person is actually required to actually plan the mission or a cockpit, anything. So, fundamentals of flight mechanics, which includes strict degree of freedom motion, the aerodynamic forces, stability, and trim analysis. So these are the four things that are basically required for the aerodynamics of. So basically, the control of the autonomous aerial vehicles. So 6 degree of freedom motion are basically three rotational motion along the X, Y, and Z axis, and three translational motion. So along the X, Y, and Z axis. So coupled together, it becomes six degrees of freedom motion, which includes three translational and three rotational motion along the axis, and basically three on one, six on one side and six on the opposite side, negative side, actually makes it a 12 instead of six. But the six are only the one governing the principles. Now the aerodynamic forces, so aerodynamic forces that are actually needed for computing the performance of aerial autonomous vehicle is basically the lift and the drag that we'll be discussing in the next class when we'll be going for the analysis. So there itself we'll be actually having a key practice note where we'll be understanding what all the other important parameters that are needed for controlling it analysis and how to actually leverage out the understanding of the same. So that is how we'll be doing it. So so yeah, that comes for the aerodynamic forces. Now the stability and trim analysis. So stability is basically when you move on the ground, traction force is the force which is acting against the road, providing friction to actually have a grip onto the ground so that the so that the vehicle does not skid when it is moving on the road. Similarly, stability is also required when the vehicle is actually moving in the air. The stability is actually two types, the longitudinal stability and the lateral stability. The lateral stability it actually includes the yaw and the roll motions, and the longitudinal stability is actually governed by the pitch motion. So these are the three things which are actually uh, governing the complete stability of the aircraft, and then the trim analysis. So trim analysis is nothing but actually helping you to understand the trimming of the aircraft, where it happens through trim. And trimming is nothing but your aircraft becomes longitudinally stable, so that there is no unwanted motion when the aircraft is moving in forward direction in the pitch axis, in the longitudinal axis. So that is if that is actually taken care of, This will happen to take care of the trimming of the aircraft. So actually, trimming is a very important phenomena which is required and necessary to actually understand when you are dealing with the aircrafts moving in the air. And when a certain perturbation is given to the aircraft when moving in the forward direction, it actually has a tendency to actually uh, damp down the moments that are being generated. So that is actually that governing principle is actually the trim analysis. So a comprehensive exploration of unmanned aerial vehicle dynamics, stability analysis, and equilibrium conditions for the graduate students, be it electronic engineer, be it aerospace engineer. That thing are there. So I have explained you all that comes here. What is 6 degrees of freedom motion? What is an aerodynamic force? What is stability and what is trim? That are those are basically a rough level of or a surface level of understanding for the moments or the moments and forces which are actually needed for the aircraft and flight dynamics analysis. Now the learning objectives. So by the end of the session, participants will develop a comprehensive understanding of the UAV flight mechanics fundamentals. These objectives from the uh, foundation for it, form the foundation for advanced control system designs and autonomous flight operations. That I told you, right? So basically, complete understanding of the flight mechanics helps you to understand the control algorithm and also on a later stage help you in designing a fully autonomous flight control system that is needed for an autonomous control system design. So actually everything is linked with each other and it lays a foundation for the same in a proper networking manner, wherein you get a proper understanding of each and every concepts properly, and then you maybe take uh, a consideration of the same in designing of an autonomous flight operation. So nothing is there in an autonomous flight operation. It is actually the design of a picksock or design of a flight control system, which has different breadboard layers, which is coded using embedded C programming, wherein you can actually plug in your pickstock and do the changes, track it, and make a certain algorithm changes, which will be benefiting your moments and forces and your flight operations. So that actually governs your autonomous flight regime of the complete profile that is actually flying in air, and it will actually govern the complete system in a proper manner. Okay, just a minute. Okay. So, first one that we discussed was the 6 degree of freedom motion. So we'll be discussing and describing the 6 degrees of freedom governing UV translational and rotational dynamics in three-dimensional space. So I told you right in the start only that basically 6 degrees of freedom is three translational plus three rotational. So three translational along the three axes x, y, and z, and three rotational along the three axes x, y, and z. Okay, so that sums up to a 6 degree of freedom motion. Right. Now the second part is the reference frame. So whenever you are generating or analyzing a complete flight uh, profile, analyzing its stability or analyzing its aerodynamic performance, you actually have a reference plane through which you'll be assessing and observing your performance of the entire flight profile system in a proper manner or in a channelized manner. So this will be actually responsible enough to actually do your entire flight mechanics review in a proper way, the proper way. And this generation of the flight profile is based on the reference plane generation. So This is nothing but, let me show you. So suppose, uh, this is your aircraft. Okay, this is your aircraft, and this is your leading edge of the wing. So this is your leading edge. Okay, and this is the place that is the center of pressure or the aerodynamic center where you observe and calculate your CL and your CD that will be doing in the next class analysis. This is the coefficient of lift and this is the coefficient of drag. So these two are the aerodynamic parameters, and then you also observe the moment. This is the pitching moment CM. Uh, this is the roll axis, and this is CM, and uh, this is the yaw axis, that is CM. Sorry, this is CL, roll axis, and this is small l. So this is C and small l. So basically, if you draw your axis, the axis here, so this is the Z axis, uh, this is the Y axis, this is the X axis. Sorry, this is the Y axis, and this is the Z axis. So along the Z axis, the motion which is there is the roll motion, is the yaw motion. Okay. Along the pitch axis, the motion which is there is the roll motion, CL, small l. And the motion along the y-axis, which is there, is this pitch motion. This is the general algorithm. Okay, this is nothing but a general algorithm that is followed in the industry, whichever industry actually designs an autonomous vehicle, basically the aerial autonomous vehicle in the aerospace industry. This is the general algorithm that is being followed. So that is what we are actually discussing out here about the roll, pitch, and yaw motion. Okay. So the plane is that only. So explaining the body fit and inertial frames, reference frames, and transformation techniques using Euler angles and quaternions. Quaternions. So quaternions and Euler angles are nothing but actually defining your uh, orientation and position of your aircraft or heading of the aircraft, and the rotation actually happening in all the axes happens through a general algorithm. So that algorithm is actually the angle by which it happens actually define the Euler angles. Okay, so that is the reference case. Third is the aerodynamic forces. So understanding generation mechanisms of lift, drag, and pitching moment through airfoil, aerodynamics, and flow physics. So that we'll be discussing in the next class in answers how to actually compute this. So understanding generation mechanisms of lift, that is the perpendicular force to the wing, the drag, the force along the motion of the along the velocity of the aircraft, the drag and the pitching moment along the y-axis that we discussed recently in the paint section, to the airfoil aerodynamics and flow physics. So yeah, now the stability analysis. So analyze static and dynamic stability characteristics specific to small unmanned aircraft configuration. So basically, we are trying to build up large aircrafts also that are autonomous in nature. But currently, we are trying to achieve that state of autonomy by using smaller aircrafts uh, and not the bigger aircraft because we are also too skeptical about it, how it will function, like it happened in the ground autonomous vehicle. But once the technology is developed and understood properly, then thereafter we will be in a position to analyze the static and dynamic stability analysis of larger aircraft segments. So that is not the key consideration of concern at the moment. Once we'll be in a position to actually do it for smaller aircrafts, we'll be much more comfortable in doing it with the larger ones. Uh, yes, Aman. Just a minute. Okay, I just started. So this one is the stability analysis. So here we will be analyzing static and dynamic stability characteristics specific to small unmanned aircraft configuration. Next is the trim and the equilibrium. So in the trim and the equilibrium conditions, conducting the trim analysis for various flight conditions, including level flight, climbs, descents, and foreign terms. So these in itself are different terminologies that are being understood. So the first one is the uh, trim that we actually already discussed that in the pitching axis or in the longitudinal axis, an aircraft is trimmed properly. So trimming happens through an elevator. So you see you see it here. So this is the horizontal tail, and the control surfaces which are here are the elevators. This is the wing, and the control surfaces which are attached to it are ailerons and flaps. So these are the ailerons, and these are the flaps. Okay. Then this vertical portion is the vertical tail, and this control surface attached to it is the rudder. So here, the one that we are discussing about conducting a trim analysis for various flight conditions, including level flight, climbs, descents, and coordinated turns. So in this condition, actually, um, the flight profiles are actually, uh, yeah, so we have discussed the trim part, right? So how the trimming of the aircraft actually governs the entire profile. Uh, the second one is including the level side, then the climbs. So climb is actually when the aircraft moves upwards in the air without changing the angle of attack, but uh, the entire pitch of the aircraft moves up. So the entire aircraft is let me show you. So the aircraft is it moves uh, uh, it moves like this. So this is the axis and this is the angle that it moves. So it moves up. So that is actually moving up, climbing up. Then a steady state level flight is actually when it moves forward, cruising, uh, and that is the case. And third is the descent when it comes down during the landing, and the coordinated turns. So during the banking, so yeah, so when the aircraft actually moves like this, turns, coming under the banking portion. Okay. So now we'll be discussing about the overview of the flight mechanics. So overview of UV flight mechanics. So, what is flight mechanics basically? So, flight mechanics is the interdisciplinary study examining forces, moments, and resulting motion of aircraft under applied aerodynamic, propulsive, and gravitational loads. Okay, so flight mechanics is the interdisciplinary study which helps you to examine the forces, moments, and the resulting motion of the aircraft when the aerodynamic, propulsive, and gravitational loads are applied. So it serves as the analytical foundation connecting vehicles, design, atmospheric physics, and control systems to achieve autonomy into the engineering part. So entire things are actually clubbed together and it makes flight mechanics. So flight mechanics is not a very easy subject. I actually worked into flight mechanics. I am a flight mechanics engineer. So it comes with a lot more understanding of different uh, physics-based topics, including the design, including the aerodynamics, including the atmosphere physics, including the control system, including the autopilot, including everything. So we have to have an understanding of propulsion. Everything is needed. So, okay. So key domain of analysis. What are the key domains of analysis? So first is the kinematics. So description of motion without considering forces, position, velocity, acceleration, and attitude evolution. So these are the parts. So description of motion without considering forces, uh, position, velocity, acceleration, and attitude evolution. So these comes under kinematics. So then comes the dynamics. So dynamics is actually the application of Newton and Euler equations relating forces and moments to translational and rotational accelerations. Okay. So these comes under dynamics. Now comes the aerodynamics part. So in the aerodynamics, it's the natural tendency of the aircraft to return to equilibrium following disturbances or maintain a steady flight. So that's what I told you, right? That is trim. Uh, we are actually trying to explain you. The generation of lift, drag, and moments through airflow interaction with vehicle surfaces. So that comes under aerodynamics. So aerodynamics is nothing but actually evaluation, and generation of lift, drag, and moments through airflow interactions with vehicle surfaces. Now comes the stability. So stability is actually the natural tendency of the aircraft to return to equilibrium following disturbances or maintain a steady flight. So that is important to stability condition to actually evaluate and maintain the natural tendency of the aircraft to return to equilibrium following disturbances or maintain a steady state flight. So flight mechanics bridges the gap between aerodynamic theory and practical flight control implementation. So understanding these principles enables engineers to design stable, efficient, and controllable airline systems. So flight mechanics is actually bridging the gap between the aerodynamic theoretical portion and practical flight control implementation. So uh, the flight mechanics part is a very important uh, part bridging the uh, aerodynamics part, which includes the lift generation, drag, and also the uh, practical flight control implementation, which helps uh, aircraft to attain autonomy. So, flight mechanics is a club of both the things. A person who is a flight mechanics engineer has to understand both the things on a close and coordinated. So, the reason why I'm explaining you these things in an autonomy class is because these things are very much important to lay a foundation of your interest towards automation. So, and you'll be having an understanding about what all things have to be learned and understood before having a clear-cut understanding about the autonomy of the system, how to design an autonomous vehicle. So, understanding these principles enables engineers to design stable, efficient, and controllable unmanned systems. So, uh, that is true that without an understanding of these concepts properly, you won't be able to design a unmanned system that that can be controlled by a complete automation or autopilot. So now we'll be discussing what is uh, a sixth degree of freedom. What is sixth degree of freedom? And yeah, so everything about it. So yeah, so now we have discussed the surface level knowledge about the sixth degree of freedom, and I'm not saying that I'll be explaining everything about the sixth degree of freedom here in this class, but at least I'll be helping you to understand because of the constraint about the timings. We and the nature of the class, which is an online mode, I cannot actually help you to have an understanding of the entire loop of the scenario in a proper way with equations. But I'll try to help you understand about the same in a proper way so that you can go home and after that you can have an understanding about the same reading books. So I'll tell you different books. So you can refer to R.C. Nelson, Robert Nelson. You can write that book, R.C. Nelson. Then you can write Daniel P. Reamer, one book. Then Snorri and Woodsman, I think. And another book is Anderson. Then one book C.W. Anderson. Then one book is Stephen Lewis. So these are some of the books that you can refer. So you can start with basic aerodynamics of J.D. Anderson, and then maybe proceed accordingly to R.C. Nelson, Snorri, and Daniel P. Reamer, and then maybe after understanding everything properly, then go to Stephen Lewis. These are the books. Okay, so let me write these. things. So just written to everyone. You can refer it from here and then you can have an understanding of the same. So every rigid body aircraft possesses six independent modes of motion in three-dimensional space. These comprise three translational degrees of freedom along orthogonal axes and three rotational degrees of freedom about those same axes. So translational motion, that is three degree of freedom, surge x-axis, sway y-axis, and heave z-axis. So in the surge, forward and backward motion along the longitudinal body axis, primarily influenced by the thrust and drag forces. Okay, so these actually helps you to so the motion along the x-axis, which actually is represented by the surge. Second is the sway, that is y-axis. In the lateral motion perpendicular to the longitudinal axis, typically minimal in symmetric flight. Okay, so that is the y-axis. So that is lateral motion perpendicular to the longitudinal axis. That is typically minimal in symmetric flights. So heave, that is z-axis. Vertical motion along the body z-axis, governed by lift, weight, and vertical thrust components. So these are the three parts in the translational motion along the three degree of freedom. Now the rotational motion, that is three degree of freedom around the rotational axis. That is roll, pitch, and yaw. The first one is the roll, that is psi, theta, and phi, theta, and psi. So this is phi, this is phi, this is theta, this is psi. So there is an entire symbolic model I could have uh, made you understand and look through it. There is an entire Simulink model using a UV toolbox in MATLAB where you can entirely design your own flight control system, um, including all the mechanical and electronics part into it. And that complete system is capable of evaluating the aerodynamic forces and then computing the moments according to it. And then it has a feedback loop mechanism which actually runs parallel to it. And that control mechanism or control algorithm is capable enough to make it a steady state level flight in the cruise condition. So that entire thing is there in that system. So first one is the roll motion. So roll motion, that is phi, is rotation about the longitudinal x-axis controlled by ailerons or differential thrust in multi-rotors. So I will tell you how. So, just a minute. Let me clean this. So in the case of roll, so okay, so that is I along the x-axis. Okay. In this condition, what happens is in the case of a fixed wing, okay, there are wings, right? So I'm doing a zoom view of it. So if you look at from the top view, you can see a wing like this, right? So these are the ailerons. That is a control surface on the wing. So these are responsible for the roll motion. So they deflect with a differential, and this deflect up, and this deflect down, for example, creating a differential lift, making it roll this side. Because this side of the wing, if it is symmetry, this side of the wing increases the lift as it increases angle of attack here. And this side, if it deflects up, it decreases the lift, and then it turns this side. And similarly, it happens this side when this side deflects down and this side deflects up. So that happens in a fixed wing. But in the case of a multi-rotor, suppose these are the configuration where this is the rotor 1, this is the rotor 2, this is the rotor 3, this is the rotor 4. So when you want to turn roll this side, so this side you increase the thrust by rotating it at a higher RPM. This side you reduce the thrust by rotating it at a lower RPM. So this will actually make your multi-copter to turn towards this side, towards the left side. And then similarly, if you want to turn to the right side, this side you increase and this side you decrease. Okay? That is how you do it. So similarly, in the case of the uh, pitch is theta. So in the case of pitch rotation about the lateral axis, that is y-axis, that is controlled by elevators or forward aft rotors thrust differential. So this also I'll help you draw. So in the case of pitch, so suppose this is your, you're viewing the aircraft from top. So suppose this is the wing, this is the tail. Okay. So these are the ailerons and this is the elevator for example. Okay. So this elevator, when the aircraft moves forward, so this elevator is actually controlling the pitching motion. Okay. Pitching motion. This is the pitching motion. So when it moves forward, moves this side or this side, and this elevator deflects down enough to actually control the moment that is being generated by this. This moment is getting controlled by this moment. So suppose CG is here, okay? CG, so this is AC aerodynamic center or CP. This is a CG. So this is a stable condition, and then this generates a pitch down moment, and due to interaction, this has a lower, and this generates a pitch up moment. So this moment is being negated by the wings moment, and then it happens to be a steady state level flight. I hope I'm clear. So, do you have any questions? We can wait for 2 minutes. So let me complete the yaw also, and then we'll take a break, and thereafter you can ask me some questions, and later on we can continue. So third is a yaw, which is actually controlled by the rudder in the vertical tail along the z-axis, controlled by the rudder or yaw moment generation mechanism. So yaw, that is psi, uh, that is rotation about the vertical z-axis, controlled by rudder or yaw moment generation mechanism. Uh, so suppose this the vertical tail, right? This is the vertical tail, and this is the rudder. Okay, so when the aircraft is seen like this, so this deflects this side and this side, actually to turn the aircraft to this and this. So it turns, if if you view the aircraft from this from back, it turns like this, and it turns like this, happens through the yawing mechanism. So, so critical coupling. So translational and rotational motions are strongly coupled in UV dynamics. For example, a pitch rotation directly affects the heave velocity, whereas roll rotation influences both sway and yaw rates through aerodynamic cross coupling effects. So, that is it. So you can ask questions for 2 minutes. I'll wait for 2 minutes, and then you can post your questions if you have. Otherwise, we'll move forward. Yeah, please. Don't have any questions? Everything is clear. Uh, XLR team, you can hear me, right? XLR team, XLR team, can you hear me? Any student, can you please respond if you can hear me or not? Co-host, can you hear me? Ishant, can you hear me now? Am I audible, right, Ishant? Okay, okay. Thank you so much. So now let me go towards the next section, that is the body versus the inertial frame references. So the accurate description of wavy motion requires two fundamental coordinate systems. That is, understanding the uh, transformation between these frames is essential for navigation, guidance, and control system implementation. That is required. So first one is the inertial reference frame, that is FI. That is definition of it is Earth fixed coordinate system, assuming non-accelerating reference that is stationary, neglecting Earth rotation for most UV applications. So origin is arbitrary ground location or launch point. Axis northeast down (NED) or east north up, that is ENU. Conventions commonly employed. Okay. So purpose is position and velocity tracking, trajectory planning, waypoint navigation, and ground-based sensor fusion. So these are the points that are important in the inertial and the application and purpose of the inertial reference frame. That is the five. Second is the body reference frame. That is FB. So definition is vehicle fixed coordinate system moving and rotating with the UAV. So these are the points that are actually changing its coordinates as per the UAV's motion. So, and the inertial frame is a fixed one. So, origin is center of gravity, CG of the aircraft. Axis is forward X, right Y, down Z, aligned with vehicle symmetry planes. Purpose, measurement of onboard sensors, i.e. new gyroscopes, aerodynamic force calculations, and control surface deflection analysis. So these are the purpose of the body reference frame. So they both are important in the inertial reference frame FI and body reference frame FB are basically very much important in the flight mechanics analysis. So the flight mechanics is a key parameter that is actually responsible for this. So coordinate transformation. So conversion between inertial and body frames utilizes rotation matrices derived from lunar angle, that is phi theta inside, or quaternions to avoid a gimbal lock. So gimbal lock is nothing but when actually the rotation matrices are aligned in such a manner that the gimbal is not aligned properly. So that phenomena is known as a gimbal lock. So the direction cosine matrices DCM relates vector components, that is VI, which includes the R vector of phi theta inside, into body velocity, where R represents a 3 cross 3 rotational matrix. This transformation is fundamental to autopilot algorithms that I was telling in the control system design. enabling sensor data fusion and command generation in the appropriate reference frames. So you understand why flight mechanics is very important because flight mechanics consists of different flight regimes, including aerodynamics and the physics of the model, and it generates a 3 cross 3 matrix with the quaternion and generating a direction cosine matrix (DCM), uh, where DCM is very much important because that transformation helps you in the autopilot algorithms, enabling the sensor data which are being fed to it in an accurate manner. So if that is not being fed in an accurate manner, your results that will be coming from it won't be accurate, and your system won't be responding to the commands that you are putting forward. Okay, so this is the case. Now, equations of motion. So, the equation of motion, that is the overview that we are giving here. So, I'm telling you the example. So, I'm telling you the physics in a very subtle manner so that you generate your own interest and study it at your own end. So that while doing an automation design of the control system, you can understand the parameters that are being talked about in a proper actual manner. And thereafter, you can take decisions on how to actually approach the problem in a proper way. Yes, for the complete dynamics of a rigid body UV are governed by the Newton Euler equations, which relate applied forces and moments to resulting translational and rotational accelerations. These equations from the mathematical foundation for flight simulation, stability analysis, and control system design. So, translational dynamics, the Newton's second law in vector form is given, which is force is equal to mass into acceleration, where sigma f is representing the vector sum of all the external forces, aerodynamic, propulsive, and gravitational. M is the vehicle mass, and A is the acceleration of the center of gravity. In components from in component form along the body axis, x-axis is fx is mass into u into qw minus rv. So this is the component in the x direction breakup. In the y-axis breakup, fy is m into v dot plus ru minus pw. So this is the y-axis breakup. Z-axis breakup is fz is equal to m into w dot plus pv minus qu. So this is the z-axis breakup. So now the rotational dynamics, Euler equations of rigid body rotation, where sigma m is equal to I omega plus omega into I omega plus omega cross I omega. So that is as a case where sigma m represents the applied moments. I is the inertial tensor, which is a 3 cross 3 matrix. Omega is the angular velocity, which velocity vector, which includes p, q, and r. And the cross product terms accounts for gyroscopic effects. Okay, so these are the things. So expanded for principal axis, that is rho is L is equal to Ix and P dot plus Iz minus Iy into Qr, which is M is Iy into Q dot plus Ix minus Iz into Pr. Here is N is equal to Iz into R dot plus Iy minus Ix into PQ. So PQR are the moments, respective moments. So intuitive understanding of this is that the equation state that acceleration results from the force imbalance, angular acceleration results from the moment imbalance modified by gyroscopic coupling terms. These nonlinear coupled differential equations capture the 6 degree of freedom of the motion of the UAV. So this is very much important. So I don't know if you're understanding it properly or not, but you have to have proper understanding of these translational and rotational dynamic motions properly to have a complete understanding of your control system design dynamics because that data actually helps you in understanding and designing of the direction cosine matrix And thereafter, that direction percent matrix is being fed into the autopilot for control system algorithm design and sensor data fusion. That helps you in autonomy. So aerodynamic forces, that is uh, lift, drag, and moment. So aerodynamic forces arise from pressure and shear stress distributions over the UAV surface as air flows around the vehicle. Understanding these forces is fundamental to predicting flight performance, stability, and control as well. So lift force L, that is capital L, where direction actually acts perpendicular to the relative airflow velocity vector, typically supporting the vehicle weight during flow. Generation results from pressure differential between upper low pressure and lower high pressure surfaces of those and lifting bodies. That is lift is half rho v square s CL, where rho represents the air density, v represents the airspeed, s represents the wing the reference area, and CL represents the lift coefficient, which is function of the angle of attack alpha. Drag force D, capital D, direction acts parallel to the relative airflow, opposite, opposing the function, opposing the flight path direction. Components, parasite drag, that is skin friction plus form drag, and induced drag, which is the byproduct of the lift generation. Whereas capital D is equal to half rho V square S into CD, where CD is the drag coefficient comprising profile drag CD naught and induced drag proportional to CL square. Pitching moment, that is capital H, where direction or rotation about the lateral y-axis causing nose up or nose down attitude changes. Origin asymmetric pressure distribution causing the net moment about the center of gravity, influenced by the wing chamber. Tail forces and CG location, that is M is equal to half rho S rho v square S C C bar, that is coordinate into CM. The C bar is the mean aerodynamic chord and CM is the pitching moment coefficient. Critical longitudinal stability. For the critical longitudinal stability assessment, the aerodynamic coefficients CL, CD, and CM are dimensionless quantities that depend primarily on the angle of attack alpha, Reynolds number, Mach number, and control circle deflection. Accurate determination through wind tunnel testing or computational fluid dynamics is essential for flight mechanics analysis. So lift curve and drag polar. Um, so you have any questions from this slide? You can ask. I'll wait for 2 minutes. You don't have any questions? Uh, I'm not saying anything. We just waiting for your questions. Do you have any questions? Okay, so let me again do the lift curve and drag polar. So in the lift, Stellar Ethic team, can you please say that you can hear me properly? It's a general request. I'm asking them so much of time. They're not replying to it. So can you please tell that you can hear me properly or not? Stellar team. Co-host, can you please say? Huh? Sorry?
Maybe you are audible.
Okay, I've been asking them so much of time for advice to actually respond to it. You can hear me properly, right?
Yes, yes, you are clear.
Okay, okay, thank you. So now we'll be discussing the lift curve and drag polar. So two fundamental aerodynamic relationships characterize aircraft performance. The lift curve relates to the lift generation, the angle of attack, and the drag polar describes the relationship between the drag and the lift coefficients. These curves enable prediction of flight envelope boundaries and optimal operating conditions. So, lift curve that is CL versus alpha, drag polar that is CD versus CL. So, um, this is the drag polar and this is the lift curve. So, linear region at low to moderate angle of attack, typically between -5 to 12 degrees for a conventional airfoil, CL increases linearly with alpha. Following CL is equal to CL naught plus CL alpha into alpha. Lift curve slope. The derivative of dCl by d alpha, typically 0.1 per degree or 5.7 per radian, that is for a symmetrical airfoil, represents the aerodynamic efficiency. So stall. Beyond critical angle of attack, alpha stall between 12 to 16 degrees. Flow separation causes abrupt CL reduction and loss of lift. Now drag polar or the CD versus CL. So parabolic relationship, drag coefficient follows CD is equal to CD naught plus KC square, where CD naught is the zero lift drag and K is the induced drag factor. Minimum drag point occurs at CL for best glide ratio, representing most efficient cruise condition. Performance metrics. Maximum L by D ratio indicates aerodynamic efficiency occurs at square root of CD naught by K. So engineering application of it is that the drag polar determines critical performance parameters, including maximum endurance speed, minimum power occurring at CL power 3 by 2 by CD, uh, which is maximum, that is the efficiency or minimum power, and the maximizing the range, that is minimum drag at maximum L by D. And so endurance is defined by CL power 3 by 2 by CD and range is defined by the L by D. So maximizing it and maximizing both the cases will actually improve your endurance and range. So UV mission planning relies on accurate characterization of these curves across the operational Notch number range. So pitching moment characteristics. So the uh, pitching moment acting on the airfoil or complete aircraft varies with angle of attack, but special reference points exist where moment behavior simplifies. So understanding these concepts is essential for longitudinal stability analysis and tail design. So CP, that is center of pressure, which is the center of pressure is the point where the resultant aerodynamic force effectively acts such that the moment about this point is zero. Key characteristics is that the CP location moves significantly with the angle of attack change mi- migrating forward as alpha increases. So this moment complicates the stability analysis. That is, the distance between the CG and CP becomes less, and that actually will pose a condition during the climb uh, where CG will come behind the AC or the CT of the aircraft, the CT of the wing, and that will result into sudden unstable characteristics. So aerodynamic center, that is AC, the aerodynamic center is the special point about the pitching moment coefficient CM remains about which the pitching moment coefficient CM remains constant regardless of the angle of attack change. Location typically at approximately 25% of the mean aerodynamic power for subsonic airfoils. Advantages are provides a fixed reference for moment calculation. Till there. So importance for longitudinal stability that we'll be discussing here. So the relationship between the aerodynamic center of pressure, and center of gravity determines the aircraft's static longitudinal stability. For positive static stability, the center of gravity must be located ahead of the aerodynamic center, that is the neutral point. Neutral point is the aerodynamic center of the aircraft. Horizontal tail surfaces generate restoring moments to counteract disturbances. The moment coefficient derivative, that is dCm by d alpha, must be negative. Slope should be that slope should be negative. In UAV design, the horizontal tail or canard canard is the horizontal tail which is ahead of the wing. Horizontal tail is the conventional tail that is behind it. So it's sized to ensure adequate stability margin, uh, maintaining control authority. So the distance between CG and AC expressed as percentage of mean aerodynamic power defines the static margin that is typically should be between 5 to 15% for conventional fixed wings UAVs. Static stability, that is fundamental concepts. Static stability describes an aircraft's initial response immediately following a disturbance from equilibrium flight. It represents the vehicle's inherent tendency to generate restoring forces and moments without pilot or autopilot intervention. Stability classifications. Positive static stability. Aircraft generates forces, moments, opposing the disturbance, tending to return toward original trim condition. Example, nose-up disturbance creates nose-down restoring moment. Neutral static stability. Aircraft remains in the disturbed state with no tendency to return or diverge further. Example, symmetric airfoil to zero angle of attack has neutral pitching moment. Negative static stability. So aircraft generates forces and moments, amplifying the disturbance, diverging further for trim from trim. Example, CG aft of neutral point causes destabilizing pitch behavior. Three axes of stability. First is the longitudinal, that is pitch. Second is the lateral, that is roll. Third, the directional, that is yaw. So longitudinal, that is pitch, is the rotation about the lateral axis determined by CG position relative to the aerodynamic center and horizontal tail contribution. Lateral, that is roll, rotation about the longitudinal axis influenced by the wing dihedral angle, sweep, and vertical fin effects. Directional or yaw, that is rotation about the vertical axis provided primarily by vertical tail fin area and moment arm. So, design philosophy, most UAVs are designed with positive static stability in all the three axes to reduce autopilot workload through Though some agile platforms intentionally relax stability for enhanced maneuverability with fly-by-wire argumentation. Okay, augmentation. So longitudinal static stability. The longitudinal static stability ensures that the aircraft neutrally resists pitch disturbances and tends to return to trimmed angle of attack. This is the most critical stability mode for fixed wing UAVs, directly affecting handling qualities and autonomous flight capability. Mathematical stability criteria: an aircraft possesses positive longitudinal static stability if and only if dCm by d alpha is less than zero, that is a negative slope. This condition states that the pitching moment coefficient must decrease with increasing angle of attack. Physically, when the aircraft pitches nose up, alpha increases. Negative nose down restoring moment must develop to counteract the disturbance. Okay. So the key design parameters. So key design parameters are: center of gravity location must be forward of the neutral point aerodynamic center of complete aircraft. Moving CG half reduces stability margin and eventually causes instability. Horizontal tail size. Tail area ST and moment arm LT contribute stabilizing moments. Larger tail volume coefficient VT, that is ST by P by SC bar, that is tail volume coefficient, increases stability. So the more your tail volume will be there, the more your elevator can work and the better the deflections could be achieved or the moments could be achieved or more deflections. Wing tail aerodynamic interaction. Downwash from wing reduces tail effective angle of attack, influencing stability derivative magnitude. That is true. So static margin. Distance between CG and neutral point typically 5 to 15% MAC for conventional designs, providing stability safety factor. Stable configuration. Negative slope ensures restoring moments. Unstable configuration, positive slope causes divergent pitch oscillation. So UAV design example: a small fixed wing UAV with 1.2 meter wingspan requires horizontal tail area of approximately 0.15 to 0.2 meter square, placed at a 0.6 to 0.8 meter aft, that is behind the wing aerodynamic center, achieving 8 to 10% static motion. Ensuring adequate neutral stability, maintaining elevator control authority to trim for trimming across the flight limit. That is a general algorithm for an example of a wingspan of 1.2 meters. The starting margin is also to 10%, which is ideal. Now, dynamic stability concept. Dynamic stability examines aircraft motion, evolution over time following a disturbance. Static stability, actually addresses initial tendency. Dynamic stability determines whether oscillations decay, persist, or grow, directly impacting flight safety and autopilot design requirements. Hmm. Fundamental dynamic stability characteristics. So dynamic response is characterized by natural frequency omega, damping ratio zeta, and time constant tau. These parameters determine oscillation period, amplitude decay rate, and settling time to steady state. Short period, that is short period mode in the dynamic stability, where characteristics are fast, highly damped oscillation in pitch rate, and angle of attack typical time period is between 1 to 3 seconds. Okay, so physics is coupling between pitch rate and angle of attack to aerodynamic pitching moment. Impact is determines initial response to elevator inputs or gust disturbance. Excessive damping causes sluggish control. Insufficient damping leads to pilot induced oscillations. Avoid mode characteristics are slow, lightly damped oscillation in airspeed and altitude at approximately constant angle of attack, typically period typical time period is between 20 to 100 seconds. Physics is exchange of kinetic and potential energy at nearly constant total energy. Impact is generally beginning due to a low frequency easily controlled by pilot or autopilot, but may cause large altitude deviations if undamped. So Dutch roll mode. So characteristics are coupled yaw roll selection combining directional and lateral dynamics. Typical period is between 3 to 8 seconds. Physics is yaw disturbance causes side slip generation, rolling moment through a dihedral effect, which in turn affects yaw through adverse yaw. In practice, must be well damped for acceptable handling. Yaw dampers commonly employed in autopilots. Roll subsidence. So characteristics are fast, non-acceleratory decay of roll rate following aileron input. So aileron actually controls the roll. Typically, time constant is lying between 0.5 to 2 seconds. So in practice, determines roll response quickness. Heavily damped mode requires large roll damping derivative. So spiral mode. Characteristics are very slow, typically slightly unstable divergence involving gradual roll and descent. In practice, time to double amplitude typically ranges greater than 20 seconds, easily corrected by pilot or autopilot, often accepted as mildly unstable in design trade-offs. Maybe specific stability considerations. The unmanned aerial vehicles present unique stability challenge distinct from manned aircraft due to their size, mass properties, propulsion system, and operational requirements. Understanding these characteristics enables effective autopilot design and safe autonomous operation. Small fixed wing UAV challenges. So low Reynolds number aerodynamics, that is RE is less than 5 lakh, results in laminar separation bubbles, reduced lift curve slopes, and large degraded stability derivatives. Reduced inherent depth, lower wing loading, and smaller moments of inertia lead to lightly damped modes requiring active stabilization. High agility requirements, that is, mission requirements often favor maneuverability over natural stability, necessitating relaxed static stability with controlled augmentation. Gust sensitivity, low wing loading makes small UAVs highly susceptible to atmospheric turbulence and wind shear. Multi-rotor specific concerns, inherent instability, that is, open loop unstable in all the axes, requiring continuous active stabilization at rates exceeding 100 Hz. Propeller gyroscope effects, that is, rotor angular momentum creates significant cross-coupling moments due to attitude changes. Aerodynamic inheritance is complex rotor to rotor and rotor to body interactions affect control effectiveness and introduce non-linearities. Center to gravity shifts. So payload mounting causes CG variations affecting control, allocation, and requiring adaptive control strategies. So these are the things that actually control your small fixed wing UAVs and multi-rotor specific UAVs. So basically, not number, inheritance damping, high agility requirement, gas sensitivity, inheritance stability, propeller gyroscope effects, aerodynamic interference, and central gravity shift. So these are the things. Autopilot comparison strategies, where modern UAV autopilots employ multiple control loops to overcome natural stability deficiencies. Inner loop, that is rate stabilization, high bandwidth feedback of angular rates, that is PQR, provides artificial damping, typically operating at 50 to 200 Hz. Middle loop, that is attitude control, maintains desired roll pitch and yaw angles through proportional integral derivative, that is PID, or model-based control. Outer loop, that is vehicle to position, uh, tracks desired flight path using GPS and inertial navigation, commanding appropriate attitude preferences. So this sophistication of autopilot algorithms allows UAVs to operate with configurations that would be unflyable for human pilots, enabling optimized designs for specific mission requirements uh, rather than adherence to classified stability margins. Okay. Rim and equilibrium, that is foundational concepts. So till this point, if anybody is having any doubts, please tell. It is a very heavy session for me as well. A lot of things are there to be helping you to understand it, and it is a very time-based, online-based course. So a lot of technical things are there. Can you please post it in the group if you have any problems? Just 2 minutes. Any doubts from your side? So okay, let me start. I think we're not listening to it, or you're not interested onto it, or I don't know why you're not asking questions. So the trim and equilibrium, and that is the foundational concepts for it. So trim represents a steady state flight condition where all the forces and moments acting on the aircraft are perfectly balanced, resulting in a constant velocity and altitude. Trim analysis forms the baseline of understanding for flight performance, defining operational limits and designing the autopilot control laws. So autopilot control laws are actually designed onto the trim mechanism methodology. So mathematical definition, a UAV is in the trim state when the sigma of force summation is zero and sigma of moment summation is zero. Okay. So this is the moment thing, and this is the fourth thing for the mathematical UAV uh, uh, complete equilibrium condition. So equivalent, equivalently, all translational and rotational accelerations are zero. So all translational and rotational accelerations are zero. That is u dot, v dot, and w dot are zero. P dot, q dot, and r dot are zero. This results in a constant airspeed, constant flight path angle, and constant turn rate. So which may be for a state and steady state and level flight. So these are the things. So common trim flight conditions are steady level flight, that is constant altitude and heading, that is lift is equal to weight and thrust is equal to drag, that is all moments are balanced. Second is the steady climb, that is constant climb rate, that is flight path angle is equal to that is constant climb rate. Gamma is equal to lift is equal to W cos gamma, which is where gamma is the flight path angle, and thrust is equal to D plus W sin gamma. Steady descent that we discussed, constant descent angle is equal to lift is equal to W cos gamma and C is equal thrust is equal to D minus W sin gamma. Right? Thrust may be reduced or idle. Uh, Now steady coordinated curve. So constant radius and altitude is N cos phi is equal to W and L sin phi is equal to MV square by R. That is centrifugal. So engineering significance of these are trim conditions serve as operating points for linearization of equations of motion, enabling stability derivative calculation and linear control system design. Autopilots typically maintain trim through small control surface deflections, that is elevated deflection delta E, aileron deflection delta A, radar deflection delta R, that vary with airspeed, altitude, and configuration changes such as flap deployment or landing gear extension. Okay. Now trim analysis example for a level slide. So this this example we'll discuss in tomorrow's class. Before that, we can do trim incline medicine. So uh, climbing and descending site represent non-level trim conditions where the thrust, drag, and lift weight relationships differ from level flight equilibrium. Understanding these conditions is essential for mission planning, energy management, and trajectory optimization. So steady climb trim and steady descent trim are the two cases where pole balancing along the flight path looks like P is equal to D plus W sin gamma and L is equal to W cos gamma, where gamma is the climb angle. For small angles, gamma is less than 15 degrees. Cos gamma is equal to 1. So lift approximately equals weight. Excess thrust P minus D determines achievable climb rate. Now R by C is equal to V sin gamma, that is P minus D into velocity by W. Key characteristics are requires thrust greater than drag. Angle of attack increases slightly due to reduced effective airspeed component. Best climb angle occurs at maximum P minus D. Best climb rate occurs at maximum P minus D into velocity by weight. Force balance occurs along the flight path as P is equal to D minus W sin gamma. Force balance perpendicular to the flight path is lift is equal to W cos gamma. For flight path less than zero is descent. In glide, flight T is equal to zero. The glide angle is T tan gamma glide is equal to D minus D by L negative is equal to minus one by L by D. Key characteristics are the thrust less than drag or zero for unpowered glide. Potential energy converts to kinetic energy, speed increase or dissipates as that. Best glide angle at minimum LBD ratio. Minimum sink rate at different airspeed than best glide angle. So energy management. Flying performance is limited by available access power. E available minus P required. Village descent can be controlled through throttle reduction, increased drag, spoilers, higher angle of attack, or forward slip maneuvers. UAV autopilots must account for these energy state changes when planning vertical trajectories to meet waypoint, altitude, and timing constraints. So we'll discuss from trim in turning slides from the next class tomorrow. And also before that, we'll be discussing the trim analysis example in the levels 9 tomorrow in tomorrow's class. So that's it from my side for today's class. I would drop it. So Excel, can I drop? I'll be leaving. So can you hear me?
Yeah, sure.
Okay. Thank you so much.
So, dear participants, I already shared the attendance complete back link in the chat box. If anybody missed on that, so please mark your attendance and share your valuable feedback about the day. So today is the day 13. We'll have two more sessions. That is tomorrow and day after tomorrow. So last session will be on a Friday. In that, we'll be having the test as well. If anybody have any doubt or any query or any question, please post me into the chat box. I will clear that. Yes, I'm resharing the attendance link. Just a moment. Yes, you can find into the chat box now. I reshared the attendance link. So Prakriti, you can just check and you can mark your attendance. Yes, today is the day 13. We'll have two more sessions. One more information which I would like to share for you guys, for your friends as well, which will be really helpful. So back to back, after completion of this program, we'll be starting two more training programs. One is for SDP on vibe coding using Gen AI tools. Okay, so that we are going to start from 27th of the October. So that is upcoming Monday. And second program after that, which we are going to start, that is a SDP on foundation of programming using C. So couple of the first year students also there. So C is a foundation for every language. So whenever we to enter into the any BTech or BCS or BCS, such kind of the CS courses, or even we are going for the computer classes as well, language courses, right? So for that as well, the base is C, where we start the thinking, where we start the developing, where we'll shape our mind, right? Where we'll start with the that thinking, development thinking, or what we can say, so flow charts and algorithms. So we'll generate the algorithms, right? So uh, just to keeping in that mind, so we are starting with one more program that is on 3rd November again. That is program title is SDP on foundation of programming using C, 3rd November. Okay, so I'm sharing the registration link here into the chat box. So this link will be work for both the programs. So you can just choose a program. If you're looking for both the programs, then you have to feed the phone 2 times. So you will get the LMS access accordingly. One more thing. So while sharing the links, you can just note that link, or you can forward in your colleges with your friends, with your colleagues. So those who are looking for a training program, okay, definitely we are always there for help. And so what about the previous class certificate? Which previous class are you asking? Previous, there are couple of previous, right? So every month, 2, 3 prior programs. So you have to help me with them. program name for the same. Mhm. Participants, any query, any doubt? Python programming. It will take us some time. You're great, sir. Thank you. About this program, Python programming. So I think we are already shared that certificate for SDP on Python programming. Okay, so you can just check. If you not received, drop an email to edil@excel.com. Our team will check on that. Where will you receive the certificate, sir? Certificate to mail only. So there is no any extra process. If your attendance is going to meet the 60%, then you will get that certificate within a 15 working days. Okay. Okay, so guys, I think almost it's 8:55. Samsung SM025. I will drop an email to everyone if anybody is facing any issue. edl@excel.com. You can note it down. You can send your email. While sending the email, then please make sure that you are now. We guys are in the era of AI, right? So we'll give the one command to the chat GPT, we'll get the answer. So write an email that I not to see the certificate of Excel enroll for the Python programming. We'll get the mail with the subject, right? But will guys not take that much efforts? We'll simply write that I not receive the certificate. But we have lots of candidates. You also know that. So whenever dropping an email, we have to be professional. So our journey is started now from the classroom to corporate, right? So in that scenario, we have to drop a proper mail, the subject line, the details, you which program you entered, your name, your email ID, your mobile number, right? In a one go only, team will check and you will get the update. This is just not for the one communication, but every communication via email or via WhatsApp, we have to be always clear. So hi, hello, again, good morning, good afternoon. I not, then again next message received, then again next message certificate. So this is something different thing. Now we have to be a professional, right? So I can refer some professional mails as well. What is be like two, what is a CC, what is a BCC, actually what is a subject, right? So most of you know that, but there are a couple of things which we can learn in the whenever we are dropping the email. So whenever you are receiving the mail from the Excel about the certificate, I hope you're getting that dear your name or dear learner, the proper subject, your certificate will be attached, your program name will be there, right? Yes, so this professionalism we have to start learning from here itself. This is the little bit GAN for today's session. I hope I'm not like boring you guys. So on this note, I think we're good to wind up the session, and we'll see you on tomorrow, same sharp at 7 o'clock. Okay, and tomorrow is the day 15. Sorry, day 14. Day after tomorrow is the day 15. We'll be having the MCQ test as well. So be prepared. Nothing is going to get from the out of box, be like out of AV or EV, whatever we covered into the last 15 days or 13 days and upcoming 2 days. So from that only there will be the quick quiz. So test your knowledge. So be ready, be prepared, and see you on tomorrow with the same energy. Till the time, take care of yourself, take care of your family, and happy learning with XLR. Bye, guys. Have a nice time ahead. And once again, a happy Diwali. Thanks.